Okay, so we saw last time that we could represent our eigenvector equation for the Hamiltonian as this differential equation. And all we want to do is solve this equation for our eigenfunctions, which are just the representation of the eigenstates in our position basis. And once we have those, we can trivially solve the Schrödinger equation. So the first thing to do to solve this is to pick out a particular problem. So we do that by picking the potential function. So in general, it's some function of x. And the first problem that everybody solves when they're going through this is the infinite square well. So there, the potential function is this kind of piecewise thing where it's just 0 inside a well, and then the walls of the well extend up to infinity at 0 and L. So the particle is basically trapped between these 2 points. And generally when, and this is not particular to quantum mechanics, this is now turned into a boundary value problem, which comes up in many areas of physics and mathematics. So yeah, generally when you have this kind of situation, what we want to do is, because we have our potential defined, it's different in different regions, we want to solve this equation in each of these different regions. And then we will kind of connect each function at these boundaries using the boundary conditions. And the usual boundary conditions that we're going to use are that our wave function should be continuous and that its derivative is continuous. So it's just kind of a nice smooth function. So for this problem, how does that work out? Well, for one thing, the reason this problem is the first one anybody solves is it works out kind of easily, because first off, the potential is infinite outside of these walls for x is less than 0 and x is greater than L, which means the particle would have to have an infinite amount of energy to get there, which is not really possible. And since the wave function, this phi, represents kind of the amplitude to find a particle at a particular point, well, if the particle can't go here, then the wave function is just going to vanish. So the first thing we can say is that phi 1 and phi 3 should just be 0. And that tells us if we want our phi 2 to be, or our wave function to be continuous, then phi 2 should be 0 at 0 and L. So inside this well, we have v is equal to 0. So our equation reduces to this. And so we're solving this subject to these boundary conditions. And this is a very easy equation to solve. It just turns into the normal, simple harmonic oscillator equation. So I can write the solution as, a cosine plus b sine of kx, where k I've just defined like this. And again, for this equation, I can either choose this as my general solution or these complex exponentials as my general solution. And they're obviously related by Euler's formula. So I can pick either one. And it really depends on the problem, whichever one you want to pick. In this one, I'm going to choose this form of the solution. So we have this, and we just need to use our boundary conditions to get the specific form of our solution. So the first condition, that phi of 0 should be 0, just tells us that a is 0. So phi should go like sine of kx. The second boundary condition is that phi of L should be 0. And for this equation, obviously there's a trivial solution where b is equal to 0, which would just mean the wave function is 0 everywhere. So that's kind of a trivial solution that we don't care about. But another way this can be satisfied is if sine of kl is 0. And we know that sine of n pi, where n pi is, or n is any integer, or 0, is 0. So we just need for KL to be equal to n pi. So it's interestingly, rather than telling us what B is from our second boundary condition, rather it gives us a constraint on the values of K. So K has to be n pi over L, where n is 0, 1, 2, 3, and so on. And since K it's basically a function of the energy, what this is saying is there are only certain values of energy that are allowed for our solutions. And those values of the energy are going to be the eigenvalues of our states, of our eigenstates. And so we know K can be written as n pi over L, so there will be an infinite number of solutions because there are an infinite number of ways we can satisfy this condition. So and we'll label our eigenstates by phi n, and they will just be B times sine of n pi over L. And obviously only from between 0 and L. Outside, phi is just 0. So we have this, and we still have this unknown constant here, this B. And this is the similar thing that happened before when we were doing our matrix stuff, is we had one undetermined coefficient, and that coefficient is going to be determined by normalization. So we know that just like last time when we were working with matrices, we wanted to normalize our state so that its norm is 1, basically. And when we worked that out, we found that we had this, when we represented our state vector as just these column vectors and row vectors, we got this equation. So we would get, C1 dagger, or C1 star times C1 plus C2 star times C2, should be C2. Oh my. So this should be 1. And now we have, obviously, our states are not represented by these vectors, they're represented by the functions, so we need to figure out how to normalize our states. And the way to do that is to rewrite this expression. So if I rewrite, the actual operation of what we're doing, we're basically doing this sum. We're summing over I of Ci star times Ci. And we're just going to make the transition from a discrete kind of thing to a continuous thing. So we know rather than these coefficients that to represent our state, we have our wave functions. So this equation will turn into this expression, that the integral of psi star times psi is equal to 1, which is just the modulus of psi squared. So our final coefficient, this b, will be determined by this normalization condition, that the integral of the modulus of this squared should be 1. So to normalize these states, we just basically calculate its norm and then find out what b should be such that its norm is 1. So if you work through that, it's not too difficult to do. What you find is that b should be square root of 2 over L. So our normalized eigenfunctions will just be these. And so we've solved our problem. We have all of our eigenfunctions. There are an infinite number of them, one for each value of n, where n can be 0, 1, 2, 3, 4, so on. And we can write our wave function, our initial wave function, as a linear combination of these eigenfunctions. So I can write at any point in time, just write my, at an initial time, as just this linear combination. And to get the wave function as a function of time, I do exactly what I did for when we were working with just the discrete bases and, columns and row vectors. All I do is, to get the size a function of time, I will just multiply each eigenfunction by this time evolution, this exponential factor. So before it's like an e to the minus I h t over h bar, and then because they're eigenfunctions, you just replace h with the corresponding eigenvalue, and which is, in this case, is en, which is just, remember k squared, we got a condition on k over here that k should be n pi over L, so that turns into a condition on e, because k is really just a function of e. So from this equation, we get that e, or solving this for e in terms of k, we get that e is h bar squared k squared over 2m, and then we know that k is just n pi. So the nth eigenvalue is just going to be h bar squared n squared pi squared over 2ml squared. So we are done, basically. We have solved our problem. So we solved this equation. We got our eigenfunctions. And then we wrote down our state as a linear combination of these eigenfunctions. And then we can find how our state evolves as a function of time, trivially just by multiplying each of these terms by the correct exponential term, which is just going to be e to the minus I en t over h bar.